Tonight, there are storms that arrive like a quiet announcement, and others that erase the edge of the world in plain sight. A blizzard is not simply a lot of snow, but a specific combination of wind, visibility, and time, measured with careful thresholds. It is a weather event defined as much by what you cannot see as by what is falling from the sky. It is snow lifted and relifted, turned into a moving curtain, until distance becomes uncertain and direction feels optional. And tonight, we'll follow the evidence gently, one calm detail at a time. Back in my office, it is quiet. A small desk lamp pools warm light across a folder with a simple label, Winter Storms. The window beside me holds a dark pane of sky and the faint suggestion of cold air beyond it. A mug sits near my notes, sending up a thin ribbon of steam that curls and disappears. My name is Madeline Rowe, and this is Blizzards for Sleep. If you'd like more calm case files like this one, you can subscribe and return whenever you need a little science and a little quiet. I open the folder slowly, not with drama, but with definitions, because winter storms are best understood when we give them the right names. And the name blizzard is one of the strictest in the weather cabinet. A winter storm can bring heavy snow, or sleet, or freezing rain. It can coat trees in glaze, or lay down soft powder, or stack ice pellets like tiny beads. It can be loud on the roof, or so quiet you only notice it when the world changes colour. But a blizzard is narrower than that broad family, because it requires a particular kind of whiteout environment. Here is the first piece of evidence written plainly. A blizzard is defined by strong winds, reduced visibility, and persistence over time. The idea is simple. Snow and wind together can make travel and orientation dangerous, even if the snow is not extreme in depth. And that difference matters, because people often remember the snowfall, while the blizzard remembers the wind. So we begin with 3 quiet questions. How strong is the wind? How far can you see? And how long does it last? Wind, visibility, and duration are measurable, which is comforting in a storm that can feel so unmeasurable when you're inside it. Wind can be observed at weather stations and inferred across broader areas by pressure patterns and terrain. Visibility can be estimated and reported, though it varies with local gusts, local snow texture, and local exposure. Duration is, in a way, the storm's insistence, the amount of time it keeps the boundary between safe and unsafe in the same place. Now, as we settle in, let's place a soft divider between 2 ideas that get tangled together. There is snowfall, which is snow coming down from above, and there is blowing snow, which is snow already on the ground, lifted back into the air by wind. A blizzard can be driven by either or both, because the defining feature is the loss of visibility in strong wind, sustained long enough to matter. I slide a page across the desk and smooth it with my palm. On it is a simple sketch. A horizontal arrow for wind, a cloud for falling snow, and a hazy band near the ground for drifting and blowing. The haze is important because it is where people lose the horizon. When the horizon disappears, distance becomes a guess, and a guess becomes fatigue, and fatigue becomes risk. So in this case file, we'll move from the large-scale setup to the small-scale details. We'll talk about how a winter storm organises moisture, lift and temperature into snow, sleet or freezing rain. We'll talk about how wind turns snow into a visibility problem and how the texture of the snow itself changes the outcome. And we'll talk about forecasting, because winter storms are a place where modern meteorology meets the reality of decisions. To make everything feel steady, I want to give you a calm mental filing system. When you hear the word blizzard, place it in a folder labelled Wind plus Low Visibility plus Time. When you hear winter storm, place it in a wider drawer that includes heavy snow, sleet, freezing rain, and combinations. And when we encounter something rare, like Thundersnow, we'll treat it as a special note clipped to the side, not the centre of the story. Now, the air outside our office window is still only an idea, but in the atmosphere, a winter storm begins with ingredients that are almost always the same at a high level. Cold air near the surface, warm and moist air somewhere above, and a mechanism to lift air so that water vapour can condense and freeze into precipitation. Lift can come from fronts, from low-pressure systems, from terrain, or from convergence bands that narrow the rising motion into long, intense stripes. The details change, but the principle does not. Air rises, cools, and forms cloud and precipitation when it reaches saturation and finds a path to grow particles. In winter, the temperature structure matters like a careful recipe. If the atmosphere is below freezing from cloud to ground, snow can survive the whole trip down. If a warm layer exists aloft, snow can melt into rain on the way down, and then refreeze into sleet if it passes through a deep cold layer near the surface. If the cold layer near the surface is shallow, rain may not have time to refreeze, and it can freeze on contact with cold surfaces as freezing rain, forming glaze ice. That's a winter storm's quiet power. The same storm can produce different hazards across a small distance, simply because the vertical profile of temperature shifts by a few degrees and a few hundred meters. And this is one reason winter forecasting is so sensitive, because a small change in the position of a boundary can change what falls, what sticks, and what becomes dangerous. Let's file one more concept before we go deeper. Meteorologists often talk about forcing, meaning the processes that make air rise. In winter storms, forcing can be broad and gentle, spreading light snow across a huge area for many hours. Or it can be narrow and intense, producing snow bands where snowfall rates climb quickly and visibility drops fast, even outside of classic blizzard winds. Snow bands are a good example of scale. The large-scale pattern may tell you a storm is likely over a region, but the exact placement of the strongest band can be a smaller scale question, dependent on subtle gradients, jet dynamics, and the evolving shape of the storm. And that smaller scale is where people experience surprise, not because meteorology is careless, but because the atmosphere is complex and the boundary lines are thin. Now we can slow down and talk about the snow itself. Snow is not a single substance, but a family of shapes, densities, and behaviours. Some snow falls as light dendrites that stack into fluffy drifts and lift easily in wind. Other snow falls as denser particles, or even rimed pellets, that pack more tightly and may be harder to loft once they settle. This matters because visibility in a blizzard is not just about how much snow is falling. It is also about how easily snow can be mobilised near the ground. A landscape covered in dry, powdery snow can feed blowing snow for hours, even after the heaviest snowfall ends. And a landscape covered in wet, sticky snow may reduce blowing snow, even while accumulating significant depth. So when we talk about blizzards, it's helpful to picture two sources of airborne snow. One source is the cloud above, falling snow in the air column. The other source is the ground. Previously fallen snow returned to the air by wind. The two can overlap, and when they do, visibility can collapse quickly, especially in gusts and in open terrain where wind has room to accelerate. If the desk lamp were a sun and my hand were a hill, we could do a small demonstration with light and shadow. In clear air, the lamp casts a clean edge on the desk. In hazy air, edges blur, contrast fades, and depth cues disappear. Blowing snow does something like that to the world outside, turning familiar landmarks into soft gradients with no clear boundary between near and far. Now, wind itself is a story with two layers. There is the wind in the atmosphere, driven by pressure differences and shaped by the jet stream, fronts, and the storm's circulation. And then there is the wind we feel near the surface, modified by friction, terrain, buildings, trees, and the roughness of the land. Surface wind can be channeled, accelerated, or shielded. So two places only a few kilometres apart can experience different levels of blowing snow, even under the same storm system. This is one reason blizzard conditions can be patchy. Not because the storm is inconsistent, but because the surface is varied. An open stretch of prairie can allow wind to stay strong and steady, lifting snow continuously. A wooded area can break the wind and reduce drifting locally, while still receiving similar snowfall. So, when we speak about blizzard climatology, the geography matters as much as the storm track. There are regions where open terrain and frequent pressure gradients make blowing snow more likely when snow is available. And there are regions where storms bring heavy snow, but wind is less likely to sustain the classic blizzard visibility criteria over many hours. Let's shift the folder slightly and look at the question of where blizzards tend to occur. In the United States, blizzard frequency has historically been highest in the northern Great Plains, in what some researchers have described as a central blizzard zone. This is not a magical line on a map, but a product of storm tracks, cold air availability, and wide open landscapes that can support persistent blowing snow when winds are strong. The pattern is a clue. Blizzards are as much about exposure as they are about precipitation. Now, I don't want the story to feel like a list of places, so we'll treat geography as texture, like the grain of paper under our fingertips. Where the terrain is open, snow can travel farther in the wind. Where the air is often cold enough for dry snow, the particles stay light and mobile. And where strong pressure gradients occur with winter cyclones, the wind can keep that snow moving, reducing visibility over long stretches of time. But blizzards are not limited to one region. They can occur in many parts of the country when the ingredients align, snow available to blow, and winds strong enough to sustain low visibility for hours. They can also occur with different storm types, including large synoptic cyclones and intense post-frontal conditions that bring strong winds across fresh snowpack. This is a gentle place to pause and let the case file breathe. We have our basic definition filed. Wind plus visibility plus time. We have our two sources of airborne snow filed, from the cloud and from the ground, and we have a quiet clue about geography filed. Open terrain and cold, powdery snow make blowing snow easier. Strong pressure gradients and storm circulation make sustained winds more likely. When those overlap, blizzard conditions become possible and sometimes probable. Now we can walk slowly through the anatomy of a typical winter cyclone, because many major winter storms are organised around low-pressure systems that move along strong temperature gradients. A cyclone is, in essence, a rotating system where air flows inward and upward, creating clouds and precipitation, while winds around the system respond to the pressure field and the balance of forces in the atmosphere. The system often has fronts, boundaries separating air masses, where lift is enhanced as warmer air is forced over colder air, or where colder air undercuts warmer air and drives ascent along a sloping surface. In winter, cyclones can produce a wide shield of snow on the cold side of the system, often north and west of the low track in many classic setups. Within that shield, there can be bands of enhanced snowfall tied to frontogenesis, meaning the strengthening of temperature gradients that intensify lift along narrow corridors. In some storms, the heaviest snow falls in these bands, and visibility can become very low even without the strongest winds, simply because snowfall rates are so high. But for a blizzard, we are interested in the combination: heavy enough snow or blowing snow, plus strong winds that keep visibility low for hours. Strong winds in winter storms often occur where the pressure gradient is tight, meaning pressure changes rapidly over distance. They can also occur in wraparound regions where the storm's circulation brings strong flow across areas already covered in snow. And they can occur behind the cold front, where cold air surges in with strong winds, creating widespread blowing snow over fresh accumulation. That last situation is worth holding gently in your mind. Sometimes the most intense blizzard visibility is not during the peak snowfall itself, but after, when the wind arrives in earnest and finds loose snow waiting on the ground. This is why people can look outside and think the storm is ending, while the most disorienting conditions are only beginning. Now, forecasting enters the folder in a calm but important way, because winter storms are a place where small errors in timing, track, and temperature profile can translate into big differences in impacts. A small shift in the storm track can move the strongest winds into or out of a region. A small shift in the rain-snow line can change whether roads are covered in plowable snow or coated in glaze ice. Modern forecasting responds to this by speaking in probabilities more often than absolutes. Instead of saying, "this will happen," forecasters increasingly quantify how likely and how confident, especially for thresholds that matter for decisions, like a certain snow amount, or a certain wind speed, or a combination that triggers hazardous travel. Let's keep this gentle, because probabilities can sound clinical, but they are actually a form of humility. They acknowledge that the atmosphere has multiple plausible futures, and that models sample those futures in different ways. When forecasters use ensembles, they are looking at many model realizations, each with slightly different starting conditions or physics, to see the range of possible outcomes. The range is not indecision, but information. It tells you whether the storm story is tightly constrained or still branching. I turn a page in the folder and see a small note I wrote for myself. It says, "Winter storm predictability depends on scale." The broad pattern may be predictable days in advance. A storm will develop, a region will be affected, cold air will be present. But finer details, like the exact placement of a narrow snowband, can be less certain, and that uncertainty matters because impacts can be concentrated in those smaller features. So, when we build this story for sleep, we'll return again and again to one soothing idea. Large patterns set the stage. Small features write the local scene. And decision support is the careful craft of translating the evolving script into guidance people can use. Now let's talk about visibility, because it is the blizzard's signature measurement. Visibility is influenced by snowfall rate, snow particle size, wind speed, and the amount of snow available for lofting near the surface. It is also influenced by lighting, because at night or in flat daylight, contrast can be low, making whiteout feel more complete even when instruments might show slight differences. In other words, visibility is physical, but it is also experienced through human senses, which can be taxed by cold, fatigue, and stress. The classic blizzard definition uses visibility thresholds to keep the term meaningful. Not every heavy snow is a blizzard, and not every windstorm in winter is a blizzard. The name is reserved for sustained conditions that make it hard to see where you are going, hard to keep orientation, and hard to travel safely. And the sustained part matters because a brief burst of near zero visibility in a gust is not the same as hours of that condition, repeated and persistent with no reliable break. Now, gently, we can fold in the idea of drifting. Drifting is snow being moved along the ground and accumulating in uneven piles, shaped by wind, obstacles, and microtopography. A drift can form on the leeward side of a fence, behind a hill, or along a road cut, where snow is deposited as wind loses speed and can no longer carry the particles. Drifts can create deep, localized accumulations that are not captured by an average snowfall measurement, and they can block roads even when surrounding areas appear less snow-covered. This matters because a blizzard is not only about what falls vertically, but what moves horizontally. A blizzard is a storm that turns snow into a fluid, a material that can be transported, piled, and lifted again, driven by wind patterns near the surface. That horizontal motion is what confuses, what isolates, and what creates the signature look of winter landscapes reshaped overnight. Now, let's let the case file drift into a calmer rhythm. I'll read you a few simple truths, one at a time, and each one can settle like snow on a glove. A blizzard is defined by wind, visibility, and duration. Snowfall alone does not define it. Blowing snow can come from the sky or from the ground. Open terrain makes blowing snow more likely when wind is strong. Large-scale patterns tell us a storm is coming. Small-scale features decide where the sharpest impacts occur. Probabilities are a way to describe what we know, and what still branches into multiple possibilities. And winter forecasting is the patient practice of watching those branches narrow as observations and models converge. Now we can move into a slower tour of storm types, because winter storm is a wide umbrella, and blizzards are just one corner of it. There are synoptic snowstorms associated with deep, low-pressure systems and widespread lift. There are lake-effect snow events where cold air passes over relatively warm water, picking up moisture and heat, and creating narrow, intense bands downwind. There are upslope snow events where air is forced up terrain, cooling and precipitating on windward slopes, sometimes producing heavy snow in persistent flow. Any of these can contribute to low visibility if snowfall rates are high. But blizzard conditions typically require strong winds, which are more common in some setups than others. For example, lake effect snow can be intense, but blizzard criteria depend on whether wind speeds and visibility reductions persist at the required thresholds. Similarly, upslope snow can be long-lasting, but wind behaviour depends on the broader pressure field and local channeling through terrain. This is why meteorology is so patient about words. A label is not just a headline, it is a statement about the physical mechanisms at work and the hazards that matter most. And when we use the word blizzard, we are pointing directly at visibility reduction in strong winds as the dominant hazard signature. Let's open a smaller envelope inside the folder, snow to liquid ratio. When snow falls, it can be fluffy and low density, meaning it takes a lot of depth to equal a small amount of liquid water. Or it can be wetter and denser, meaning a smaller depth contains more water content. The ratio depends on temperature profiles, crystal habits, and microphysical processes like rimming, where supercooled droplets freeze onto snowflakes and change their shape and density. Why do we care in a blizzard story? Because low-density snow is easier to loft and keep suspended, increasing blowing snow potential after it accumulates. And denser snow may reduce lofting, but can increase snow load impacts, like stress on trees and structures, depending on accumulation and wind. So, in winter storms, density is a quiet variable that influences both mobility and weight, both visibility and infrastructure strain. Now I'll let the desk scene return, just for a moment. A pencil rests beside the folder, and I turn it slowly between my fingers as if it were a tiny weather vane. Outside, the world is still dark, but in our mind's eye, the atmosphere is busy, moving water through phase changes, moving air through pressure gradients, and moving snow across the ground like a pale current. When storms are described in forecasts, they often come with thresholds, and thresholds can feel abrupt, like a line drawn through a continuous world. But thresholds exist because decisions exist. Road crews need to plan staffing and equipment staging. Utilities need to anticipate line damage risk when wind and ice combine. Hospitals, schools, and public transit need to make choices, and choices benefit from clear categories, even though the atmosphere itself does not switch on and off like a light. This is where decision support services enter the story. The goal is not only to predict the weather, but to communicate risk in a way that matches how people act in the real world. Probabilistic products, ensemble guidance, and impact-based indices are all tools to translate physical uncertainty into decision-relevant information. And in winter storms, where small shifts can produce big consequences, those tools matter especially. One modern approach is to emphasize the likelihood of exceeding thresholds rather than giving a single number as if it were certain. Instead of 10 inches, you might hear a high chance of at least 6 inches and a moderate chance of at least 12, which helps people interpret the tail of the distribution, not just the most likely outcome. Another approach is to describe impacts directly, such as the risk of hazardous travel due to blowing snow, or the risk of power outages due to heavy wet snow and wind. In some settings, decision support products combine multiple ingredients into categories, recognizing that people experience a storm as a bundle of hazards, not as separate graphs. Now we can gently move into the part of the file that deals with whiteouts, because whiteout is often used casually, but it has a physical basis in visibility and contrast. In a whiteout, the scattering of light by airborne snow and cloud can remove shadows and depth cues, making the world look uniformly bright or uniformly pale. When that happens, people can lose orientation because the brain relies on contrast and edges to infer distance and shape. In blizzard conditions, blowing snow near the surface can act like a moving fog, and the motion itself can make it even harder to stabilize your sense of direction. It's important to remember that visibility can vary rapidly in a blizzard because gusts fluctuate and snow transport is uneven. So conditions can alternate between barely manageable and completely opaque over minutes, which is exhausting and dangerous for travelers because the environment is unpredictable in the most immediate way. Now, because this is for sleep, we'll keep our tone calm and factual, not urgent. But it is still respectful to note that the blizzard definition exists because these conditions have repeatedly produced serious travel hazards. The science is quiet, but it is not abstract. It has been written into public service warning criteria for a reason. Let's take another soft drift, like a slow breath in a cold room. Wind, visibility, duration. Those are the three keys on the ring. Snowfall rate matters. Snow texture matters. Ground snow availability matters. Terrain and exposure matter. Large-scale patterns set the storm's boundaries. Small-scale bands and gradients sharpen the experience. Forecasts use ensembles because the atmosphere has more than one plausible path until it chooses one. And decision support is the practice of speaking about that choice before it is fully made. Now let's talk about how meteorologists study blizzards over long periods, because climatology helps us understand what is typical, what is rare, and where the risk tends to concentrate. Climatology is the slow science of counting and mapping, building a portrait of events across decades so patterns emerge from noise. In blizzard studies, researchers often use station reports and definitions based on wind and visibility to identify events, then analyse frequency, seasonality, and regional clustering. This work shows that blizzards are not distributed evenly across the country, and that the northern plains stand out as a region of particularly frequent events in historical records. Seasonality also matters. Blizzards are most common in the cold season, but their timing within winter can vary by region and by year, influenced by storm tracks, cold air outbreaks, and the availability of snow to blow. In some areas, early winter storms can produce blizzard conditions if strong winds follow a fresh snowfall. In others, late winter and early spring can still produce blizzards when strong systems move through, and cold air remains in place, even as daylight returns, and the calendar feels like it should be softening. There are also links, sometimes subtle, between blizzard frequency and broader climate patterns like ENSO, though such relationships can be weaker or region-dependent compared to more direct storm-to-storm mechanisms. For our purposes tonight, the key idea is simply this. Blizzards are part of a climate system that has both variability and structure, and climatology helps us see that structure calmly. Now we can turn toward a more modern question. How might blizzard occurrence change in the future? And how do scientists even measure that in climate model data? This is a gentle but important point. A traditional blizzard definition depends on visibility, which is not always directly represented in global climate model outputs. So researchers often treat blizzards as a compound event, combining proxies like heavy snowfall and strong winds over a certain duration to approximate the conditions that would produce low visibility. This approach does not weaken the science, it clarifies it. It says, we cannot directly compute visibility everywhere, so we define a physically grounded proxy based on the ingredients that control it. Then researchers can ask whether the frequency of those ingredient combinations increases or decreases under different scenarios. Many projections suggest decreases in blizzard-like events in some regions, often because warming reduces the number of days cold enough for snow and shifts precipitation toward rain, while wind changes can also affect the overlap of strong wind with heavy snow conditions. This is not a single, simple story, because winter storms will still occur in a warming world, but their character can change. The balance between snow, sleet, and freezing rain can shift. The geographic zones of typical hazards can move, and the compound overlap that produces classic blizzard conditions can become less frequent in some places, even while heavy precipitation events remain significant in others. Now, because we are keeping this as a sleep story with hard science, we will treat climate as a calm background layer, not as a heated argument. The key is that scientists use careful definitions and proxies to study rare events across long timescales, and they report trends with an awareness of uncertainty, regional variation, and the limits of what models can represent directly. Let's return to forecasting again, but more slowly, and with a focus on what makes winter storms uniquely challenging for operational meteorology. First, precipitation-type transitions can be sharp and highly sensitive to temperature profiles near freezing. Second, narrow bands of heavy snow can produce strong gradients in accumulation over short distances. Third, the wind field can evolve quickly as pressure gradients tighten, lows deepen, and fronts surge, changing the timing of blowing snow hazards relative to snowfall. When forecasters talk about ensembles, you can picture a stack of plausible atmosphere snapshots, each one a little different, like a deck of cards shuffled from nearly the same initial arrangement. If most cards show the low tracking north, confidence increases that the north track is likely. If the cards spread out, the future is still branching, and a single deterministic forecast could be misleading if presented without context. This is why probabilistic guidance is so useful for winter storms, because the difference between a near miss and a direct hit can be only a small shift, but the impacts can be very different. There is also a concept in ensemble forecasting called spread, meaning how varied the outcomes are across ensemble members. Sometimes ensembles can be underdispersive, meaning they cluster too tightly and fail to capture the full range of possibilities, which can lead to surprise when the real storm falls outside the predicted envelope. The response to that is continuous improvement, better observations, better data assimilation, better model physics, better representation of snow microphysics, boundary layer processes, and the coupling between wind and snow transport near the surface. It is a long arc of refinement, and winter storms are one of the laboratories where that refinement matters deeply. Now I'll offer a gentle, almost meditative way to think about a forecast map. A deterministic map is a single painting. An ensemble is a gallery. The gallery shows you what stays the same across paintings and what shifts and where your eye should linger, because that's where the uncertainty lives. And then decision support is the label beside the gallery that says quietly, here's what this means for you. Not as a command, but as information aligned with action, travel risk, timing of worst conditions, probability of thresholds, and confidence in key hazards like blowing snow or ice accretion. Now, with that in mind, let's tuck in one more modern concept: impact-based indices for winter storms. Some tools combine predicted snowfall, wind, temperature, and other ingredients to estimate the potential for impacts like difficult travel or power outages. These are not replacements for the underlying forecast, but translations of it into risk categories that can be easier to digest, especially when multiple hazards overlap. They reflect the reality that people experience a storm as a whole environment, not as separate graphs for snow, wind, and temperature. Now, I want to keep our pace slow so we won't get lost in product names or operational details. We'll keep the principle. Modern winter storm communication often shifts toward probabilities and impacts because the atmosphere is uncertain in the details and decisions depend on thresholds. Let's let the office return again. The folder is open to the middle now, pages gently fanned like a quiet deck of cards. The lamp hums softly, the kind of sound you only notice when everything else is still. And outside the window, our imagined winter keeps moving. Wind and snow, writing patterns you can't quite predict by eye, but can understand by mechanism. Now we can slip into one of the rarest subfolders in the file, Thundersnow. Thundersnow is exactly what it sounds like: lightning and thunder occurring during a snowstorm. It is uncommon because thunderstorms usually require instability and a warm, moist boundary layer, while snowstorms typically occur in colder, more stable environments. So thundersnow happens when the atmosphere briefly aligns cold precipitation with enough convective strength to produce charge separation and lightning, often near intense bands or rapidly deepening systems where lift is strong. Thundersnow is often reported in association with heavy snowfall rates because strong upward motion supports the kind of mixed phase cloud microphysics that can generate electrical charging. The thunder can sound muffled by snow, and lightning can appear strangely bright against a pale, snowy background. But even here, we keep our focus on the mechanism: strong lift, enough instability in a layer, and cloud processes that allow charge to separate and discharge, all occurring while the surface environment is cold enough for snow. We don't need to linger too long here. It's a fascinating note, a rare stamp on the case file, but it is not the core of the blizzard story. So we'll clip it back to the side and return to wind, visibility, and time, where the main evidence lives. Now, as the script continues, we can let it drift through a series of calm walkthroughs that revisit the same concepts from different angles, each one soothing and reinforcing without feeling repetitive. Here is a walkthrough of a classic scenario. A low-pressure system approaches a region with cold air already in place at the surface. Moist air is lifted along a frontal boundary, cloud thickens, and snow begins to fall, sometimes lightly at first, then more steadily as lift strengthens. Accumulation starts to cover the ground in a uniform layer, and the world becomes quieter as snow absorbs sound and softens edges. Then the pressure gradient tightens as the storm deepens or as the low passes nearby. Winds increase, gusts become more frequent, and the snow on the ground becomes available for transport. Visibility drops in bursts, then stays low more consistently as blowing snow fills the near-surface layer and turns headlights into diffuse halos. If the wind and low visibility persist for hours, the event crosses from snowstorm into blizzard, not by feeling, but by measurable criteria. Here is another walkthrough, quieter and more subtle. Snow falls earlier in the day, leaving a fresh, dry layer across open terrain. The snowfall itself may taper, and someone might think the storm is over. But behind the system, cold air surges in with strong winds, and the fresh snow becomes airborne again, even under skies that are beginning to clear. In that case, blizzard conditions can occur without active heavy snowfall overhead, because the hazard is driven by wind-driven snow transport from the ground. Visibility can become very low, even though the clouds are thinning, because the near-surface environment is filled with snow in motion. This is one of the most counterintuitive aspects of blizzards, and one of the reasons the definition emphasizes visibility and wind rather than snowfall alone. Now, a third walkthrough focused on banding. A broad storm shield spreads across a region, but within it a narrow band forms where lift intensifies along a strengthening temperature gradient. Inside the band, snowfall rates increase sharply and visibility drops, while outside the band, snow is lighter and conditions are less severe. If strong winds coincide with the band and persist, blizzard conditions can be localized along a corridor, creating sharp differences in travel conditions across short distances. This is where forecasting becomes both science and communication. Forecasters may have high confidence in a storm impacting a region, but less confidence in the exact placement of the strongest band until closer in time, when observations refine the picture. That is why probabilistic maps and careful phrasing matter, because they can express a zone of higher risk rather than a single thin line that implies certainty beyond what the atmosphere has granted. Now, I want to give you a soft set of case notes, like labels on specimen jars, each one short enough to rest in the mind without effort. Pressure gradients drive wind. Wind transports snow. Transported snow reduces visibility. Reduced visibility defines the blizzard hazard. Temperature profiles shape precipitation type. A warm layer aloft can melt snow into rain. A deep, cold layer can refreeze rain into sleet. A shallow, cold layer can freeze rain on contact as glaze ice. Snow density influences both drifting and load. Dry snow lofts easily. Wet snow weighs more. Wind interacts with both in different ways. Now we can let the remainder of the episode expand naturally, like a long hallway with several open doors, each leading to a quiet room of related science. We'll step into each room slowly, and we'll leave without any abrupt announcements, letting the transitions feel like a gentle continuation of the same calm investigation. Let's step into the room labelled boundary layer, because the lowest part of the atmosphere is where the blizzard is felt, and where blowing snow lives. The boundary layer is shaped by friction, surface roughness, stability, and turbulence. In cold conditions, stability can increase, which can suppress vertical mixing, but strong winds and rough surfaces can still generate turbulent gusts that loft snow intermittently. The result can be a near-surface layer of snow transport that pulses, thickens, and thins, making visibility a moving target, even at a fixed location. Surface roughness matters in a calm, practical way. A smooth, open field can allow wind to accelerate and sustain higher speeds near the ground. A forest canopy increases roughness and can reduce near-surface wind, lowering blowing snow potential locally, though it can also create turbulence at edges and clearings. Human structures can channel wind through corridors, creating local jets that increase drifting in specific places, like along the leeward side of a building or across an exposed bridge deck. This is why storm impacts can be so uneven. The atmosphere provides the wind field, but the surface shapes how that wind is delivered to the snowpack. And the snowpack provides the material, but its temperature and texture determine how easily it breaks into particles that can remain airborne. A blizzard is, in a sense, a coupling between atmosphere and surface, mediated by physics that is both elegant and stubbornly local. Now, let's step into another room labelled observations, because modern forecasting is anchored to what we can measure. Weather stations provide wind, temperature, pressure, and sometimes visibility estimates, but the atmosphere is not fully observed everywhere at all times. Radar can detect precipitation structures and banding, but blowing snow near the surface can be harder to capture directly, and radar beams sample higher levels as distance increases from the radar site. Satellite imagery provides broad cloud patterns and moisture signatures, but near-surface visibility reduction is a challenge to infer, especially under thick cloud and during night in high latitudes. This is why data assimilation is so important. Forecast models begin with an estimate of the atmosphere's current state, built from many observations blended together in a physically consistent way. The better the initial state, the better the model's chances of staying close to reality as it evolves forward in time. But even with excellent data, the atmosphere remains sensitive, and winter storms often contain mesoscale features that can amplify small differences into meaningful local changes. Now, another room? Snow bands and frontogenesis, because this is where winter storms often concentrate their most intense snowfall. Frontogenesis is the strengthening of a temperature gradient, and when a gradient strengthens, the atmosphere responds with a circulation that includes rising motion on one side and sinking on the other, enhancing precipitation along a narrow region. In a winter storm, this can produce banded structures where snowfall rates increase, sometimes dramatically, over a relatively narrow swath. These bands can pivot, shift, or redevelop as the storm evolves, and their exact placement can be one of the least predictable, yet most impactful, aspects of a storm forecast. When heavy snowfall rates occur inside a band, visibility can drop even with moderate winds. If strong winds are also present, the combination can be severe, producing rapid onset of near whiteout conditions and a long duration of low visibility if the band is persistent, or if blowing snow continues after the band moves on. Now, a room labelled lake effect, because it is a winter phenomenon that is both simple and intricate. Cold air moving over relatively warm water picks up heat and moisture from the lake surface. That added moisture and heat can destabilize the lower atmosphere, promoting convection and cloud formation, often organizing into narrow snowbands aligned with the wind direction. Downwind, the air rises, cools, and precipitates as snow, sometimes producing intense local snowfall, while nearby areas see much less. Lake effect events can produce very low visibility in heavy snow, and in some cases, strong winds can also produce blowing snow. But whether blizzard criteria are met depends on the persistence and wind thresholds across the required duration. So, once again, we return to the same keys: wind, visibility, and time, filed carefully, used consistently, and never rushed. Now, a room labelled human factors, not because we are leaving science, but because the impacts of visibility and wind are filtered through perception and behaviour. Cold reduces manual dexterity and can slow response time. Fatigue increases when navigation becomes uncertain, and when conditions fluctuate between glimpses of clarity and sudden opacity. Decision-making under uncertainty is hard, which is why clear communication and simple criteria are valuable, and why forecast messaging often emphasises timing, when conditions are expected to worsen, when they may peak, and when they may improve. Now we can let the script drift into a long, soothing recap, because repetition is a kind of comfort when it's gentle and purposeful. A blizzard is a measurement-based label. It is not just a feeling. It is wind, visibility, and time, aligned in a sustained way. Snowfall contributes, but blowing snow can be just as important, sometimes more. Winter storms are a broader category. They include heavy snow, sleet, freezing rain, and combinations. Their hazards come from phase changes and temperature profiles, from wind and icing, from drifting and reduced friction on roads. And their forecasts are sensitive because small shifts can change precipitation type, accumulation distribution, and wind timing. Forecasting has improved through observations, modelling, ensembles, and decision support services. Probabilities communicate branching futures with honesty. Impact-based messaging helps people translate meteorology into choices. And behind every map is the same physics: air rising and cooling, water changing phase, wind responding to pressure, and snow responding to wind. Now, the rest of our night can be spent in the slow, steady rhythm of those physics, described in different ways, so your mind can rest on them the way it rests on a familiar melody. We can talk about the jet stream softly, because it often plays a role in winter storm development and intensity. The jet stream is a ribbon of fast winds high in the atmosphere, shaped by temperature gradients between air masses. When the jet stream structure supports divergence aloft, air can be encouraged to rise below, helping surface low pressure to deepen and storms to intensify. In winter storms, jet dynamics can influence where lift is strongest and where storm tracks favour development, though the storm is still constrained by the temperature and moisture structure near the surface and throughout the troposphere. We can talk about moisture transport because snow begins as water vapour, borrowed from oceans, lakes, and distant air masses, then carried into colder regions where it becomes ice and falls as snow. Atmospheric rivers are more commonly discussed for rain and flooding, but the idea of focused moisture transport also matters in winter storms, where strong flow can deliver water vapour into a cold environment and produce heavy snowfall when lift is present. We can talk about the quiet mathematics of phase change. When water vapour condenses or deposits onto ice, latent heat is released, subtly warming the surrounding air and influencing buoyancy and stability. When melting occurs, energy is absorbed, and the temperature of the melting layer can be pinned near freezing for a time, creating sharp transitions between snow and rain that persist until the energy balance shifts. These details are small, but they matter, because winter storms often live near the freezing point, where tiny energy differences decide whether the precipitation reaches the ground as snow, sleet, or freezing rain. And we can talk about snow crystals because they are a slow poetry of physics. A crystal's shape is influenced by temperature and humidity, leading to different habits: plates, columns, dendrites, needles. Dendritic growth tends to occur in certain temperature ranges with sufficient supersaturation, producing intricate branches that trap air and create low-density snow. That low-density snow can drift easily, contributing to blowing snow and visibility reduction when wind arrives, which ties the microscopic shape back to the macroscopic experience of a blizzard. Now, another long, gentle recap, with slightly different phrasing, so it feels like a new angle on the same truth. Blizzards are a partnership between atmosphere and surface. The atmosphere provides wind and falling snow. The surface provides loose snow to be lifted and carried. The boundary layer decides how efficiently the wind can grab that snow and suspend it in the air you breathe. The most disorienting part is not always the heaviest snowfall, but the persistence of low visibility under strong wind, minute after minute, hour after hour. That persistence is why the definition includes time. Time turns a difficult moment into a sustained hazard environment. And time is what transforms weather into an event that must be planned around, not simply observed. Now we can let the last part of the episode become a gentle filing away, where Madeline closes the folder gradually, summarising each section as if placing documents into labelled drawers. First drawer. Definitions: blizzard equals wind, low visibility, and duration. Winter storm equals a broader set of cold season precipitation hazards. Words matter because they map to mechanisms and impacts. Second drawer: mechanisms. Lift makes precipitation. Temperature profiles decide type. Wind moves snow sideways and upward from the surface. Visibility falls when snow fills the air and the horizon dissolves. Third drawer: geography and climatology. Some regions see blizzards more often because storm tracks, cold air, open terrain, and snow availability overlap. Patterns emerge over decades, revealing zones of higher frequency and typical seasons of risk. Fourth drawer: forecasting and decision support. Winter storm forecasts are sensitive to small shifts. Ensembles show branching possibilities. Probabilities and impact-based messaging help translate uncertainty into choices. Side note clipped to the file. Thundersnow. Rare? but physically explainable. A sign of strong lift and charging processes inside a snowstorm environment. Now, the folder can begin to close, not with a snap, but with a slow press of paper against paper, as if the case file is settling itself back into the cabinet. The desk lamp still makes a small island of light, but the edges of the room are soft and quiet. Outside the window, the winter night remains, vast and patient, full of moving air and drifting snow that follows physics, even when it feels like mystery. Before we finish, I'll leave you with a final, gentle loop of the key idea, a lullaby made of measurement and mechanism, wind, visibility, duration, that is the blizzard, lift, moisture, temperature profile, that is the winter storm's engine, ensembles, probabilities, impacts. That is how we speak about uncertainty with care. And now, with the folder closed and the lamp dim, you can let the rest of the details drift away, like snow settling after the wind eases, leaving the world cleanly outlined again, one quiet edge at a time.